Jnanam Paramam Dhyayam. Knowledge is supreme.
Welcome to the 7th lecture of the course titled Advanced Transition Metal Organometallic Chemistry. In our previous lectures, we have been discussing very important topic, which is cyclobutadiene as a ligand for transition metals in organometallic chemistry. In this context, in the last class, we have looked at the structure and bonding of this cyclobutadiene ligand and what are the issues that concerns the nature of cyclobutadiene ligand, how does it bind to transition metal, what kind of structure would it exist, what kind of reactivity would it exhibit. All of these we try to understand with respect to its molecular orbital diagram, and these molecular orbital diagrams were constructed from atomic orbitals of cyclobutadiene ligands, and then we had seen these fragment molecular orbitals or FMOs constructed from the atomic orbitals represents a diradical nature of cyclobutadiene in its neutral form and square geometry, which sort of makes it extremely reactive. However, upon complexation to transition metal, the cyclobutadiene accepts two more electrons from its metals orbital, resulting in a aromatic configuration of 6 pi electron and then getting stabilized in its transition metal complexes. So, these molecular orbital diagram that we had looked at, we had not only looked at for cyclobutadiene, but also had compared it with just butadiene as well as allyl radicals that we have discussed in our earlier classes. Towards the end of last lecture, we have also looked at various preparative methods available for the preparation of transition metal cyclobutadiene complexes, and today in this lecture we are going to continue upon these various synthetic schemes that are available for preparing the metal cyclobutadiene complexes. First method that we had looked at involved the reaction of cyclobutadiene with two halogens, dihalogenated cyclobutadiene, and looked into the dehalogenation by reaction with nickel carbonyl, resulting in nickel chloride and the half sandwich transition metal cyclobutadiene complex, as we had seen earlier. Now, in this class we will see another example of along the same theme, in which iron complex of cyclobutadiene was prepared along the same lines. So, this preparation is about preparation from dehalogenation of dihalocyclobutene. So, this is a dihalocyclobutene, reacting with iron 0 precursor Fe2CO9 and also eliminates FeCl2 giving cyclobutene, Fe, cyclobutene, and this is again a planar structure. Ring, diamagnetic, this has 18 valence electron. So, 4, 8, 12 and 6 from 3 COs. This is a 18 valence electron compound and hence very stable. It has a CC bond distance of 146 picometer and melting point of 26 degrees centigrade. This was synthesized by Petit in 1965. So, this method is similar to the nickel carbonyl method and also follows the same strategy of preparing this cyclobutadiene transition metal complex from this dihalocyclobutene by reaction by dehalogenation with a nickel 0 carbene precursor. The second method involves preparation from that uses dimerization of alkynes. The reaction of Cp, this is the Hopf sandwich complex, CpCO carbonyl reacting with alkyne in presence of heat giving a sandwich compound along with trimerization. So, dimerization will give cyclobutene of this alkyne and trimerization will give benzene. So, what we see that one synthesizes a sandwich compound, a sandwich complex, the classification that we had spoken about, from a half sandwich cobalt complex in that classification. Both are also a 18 electron species. This is 5, 9 and 4. So, this is a 18 valence electron species, as well as the cobalt precursor is also a 18 valence electron species, 5, 9 and 2 carbonyls 4. So, this also is a 18 valence electron species along with the formation of benzene. So, this is a nice example where we saw that dimerization or trimerization of alkene leading to the synthesis of cyclobutene, and that is stabilized by complexation with Cp carbonyl fragment with the results of elimination of 2 carbonyl moiety, giving this heteroleptic sandwich complex. The same route is used is another preparation that also involves dimerization of alkynes. So, here the reaction of Na2PDCl4 plus 2 alkynes in ethanol gives this tetraphenyl cyclobutadiene complex of palladium chloride and this also 18 electron compound 4 plus 10 14 and 2 chloride single bonded. So, this is 1 electron each, 2 together 16 and then 1 dative plus 2. So, this also is a 18 valence electron compound, and based on the classifications that we have been studying, this falls in the category of half sandwich complex. Cyclobutadiene complex can also be prepared by ligand transfer reactions. For example, the reaction of the palladium tetraphenyl cyclobutadiene with FeCO5 gives the corresponding cyclobutadiene complex of iron. So, here we see a lateral ligand transfer, from palladium to iron, and this as if that this is a lateral gliding or transfer of cyclobutadiene ligand from one metal, which is palladium, onto another metal, which is iron. So, this is sort of can be perceived as a ligand exchange reaction, and also a very useful method for producing these metal cyclobutadiene complexes. So, the another method is preparation of cyclobutadiene from metallocyclopentadiene complexes. So, this is a very interesting example where cyclobutadiene is constructed from metallocyclopentadiene complexes. and this preparation occurs by ring contraction. The example is a teen metallocyclopentadienyl complex. Giving rise to this nickel bromide plus Me2SN polymer. So, this ring contraction is kind of a very elegant way where a metallocyclopentadiene, this is why it is metallocyclopentadiene, because there is a cyclopentadiene ring, 5-membered ring containing one of the vertices is a metal. So, it is metallocyclopentane, and then it is diene because there are 2 double bonds. So, the method uses the concepts of extracting the metal out, so resulting in cyclobutadiene, and then coordinating that formed cyclobutadiene by extraction of the tin to nickel bromide, giving rise to this structure. So, this is in terms of synthetic aesthetics, this is a very elegant way of synthesizing this cyclobutadiene ring, and as we progress in the field of organometallic chemistry, look at different strategies people have employed in creating these complexes, one cannot but stand back and appreciate the beauty and the aesthetic and the complexity of the synthesis people have undertaken in order to reach their destination. And in this particular example is one such a very elegant example where ring contraction of metallocyclopentadiene having a tin have been performed to get to the cyclobutadiene ring. I must also mention that this metallocyclopentadiene having a tin or any other metal in one of its vertices itself is a very exotic organometallic compound and also requires lot of synthetic skills and challenges in trying to synthesize them. So, this is a very nice example of beautiful chemistry that is being played out in the field of organometallic chemistry. We are going to take a look at another such elegant example along the same lines that involves ring contractions by metallocyclopentadiene, and in this case this is with aluminum. This gives over here again this aluminum based metallocyclopentadiene undergoes those loss of aluminum and then resulting in cyclobutadiene ring that then coordinates to nickel to give this binary cyclobutadienyl complex. A beautiful example. So, this is the first binary complex cyclobutadienyl complex. And was synthesized by Hoberg. In 1978. So, this again in the nomenclature would be a sandwich complex, and this also is a 18 valence electron compound. 4e 10e 4e is 18 valence electron compound. Another method uses decarboxylation of photo alpha pyrone. So, this is also an elegant chemistry as is outlined over here. In presence of light, it gives this intermediate. And that loses carbon dioxide in presence of FeCO5. So, this moiety, this carbon dioxide moiety is lost, and as a result one gets this cyclobutadiene. So, this CO2 is lost and there is a bond formed over here with FeCO3, and the reaction also goes little bit backwards, and one also isolates these alpha pyrone compounds of iron carbonyl as well. Both of these are 18 electron compounds. So, 4 electrons, and this iron is 8 electrons and this is 6. So, these are 18V compounds, and this intermediate can also react with Cp cobalt dicarbonyl. In this case eliminates carbon dioxide, resulting in cyclopentadienyl cobalt cyclobutadiene. So, the cobalt carbon distance is 204 picometer, and for this cyclobutadiene cobalt carbon distance is 197 picometer. The CC bond is 139 picometer, and this one is 143 picometer. So, this also is a very interesting example where by using light one generates this very highly unstable intermediate, and that releases carbon dioxide with the generation of cyclobutadiene, and that can be complexed with iron carbonyl to give this half sandwich compound. half sandwich compound, and can also react with CP cobalt dicarbonyl to give the sandwich compound. So, with this I would like to come to the end of today's class, in which we have looked at various preparative methods that are available for preparation of transition metal cyclobutadiene complexes. To reiterate that we have come across some of the very elegant examples in which one can see the ring contraction leading to this. Some can also use organic molecules like alpha pyrons and use light and then subsequent trapping with metal carbonyls, and to make these cyclobutadiene transition metal complexes. One also uses the strategy of simple ligand transfer from one metal to another metal for preparing these cyclobutadiene transition metal complexes. And first we had also seen the use of dehalogenation of dihalocyclobutene for preparation of these complexes. So, with this we come to the end on our discussion on various methods used for preparing this cyclobutadiene transition metal complexes, and in the next class we would be discussing about various reactivity that these transition metal cyclobutadiene complexes exhibit. These are interesting class of compounds and would lead to very interesting reactivity that we would see in the next lecture. Till then, goodbye and thank you.